Welcome to the Drag Force Lab by Josh Whitley. As an introduction, the purpose of this lab is to predict the movement of a falling object subject to drag using a Python model. We rely on the equation FD equals BV, which means force drag equals the drag coefficient, B, times velocity. Terminal velocity is defined as when the net force of a falling object equals 0. In other words, mass times gravity minus the force drag equals 0. There were 5 major lab components: the initial video, the raw tracker data, the Python model without drag, the Python model with drag, and a chart of comparisons of the raw tracker data Python models with and without drag. If we go to our tracker video, we'll see that it shows Nathan dropping a stack of coffee filters. It takes about 1.533 seconds to happen, and over here in the bottom right of tracker, you'll see that our T and Y position, which are the only two things we care about, are displayed down here. Now those data points were exported to Excel. It's highlighted over here on the left. And we created a Python model to attempt to mimic this motion. So we set all of our parameters to be appropriate for the lab. For example, the ball mass was set to 0.00625 grams. There was no initial velocity, so we're going to set that y component of the vector to 0. And the time elapsed is 1.533 seconds, as determined by how much time our tracker video ran. And this was run and export in time versus y position in centimeters to this Excel spreadsheet. It's represented right here. That was with drag. Now, without drag, all we had to do was take the b value in our Python code and set it to 0, and that's represented right here. Now, this data is used to make this comparison chart. The tracker raw data is represented by blue diamonds, and the Python with drag is represented by red squares. As you can see, they're extremely close to one another. And they have a change in the y position that is linear, which means their velocity is basically immediately constant. It reaches terminal velocity extremely quickly. The Python without drag is moving quadratically in the negative direction, which means that its velocity is linearly increasing, which means that it has a constant acceleration, which means that it does not reach terminal velocity. That sort of answers the what does it mean question of this lab. So the model that predicts a terminal velocity is the Python with drag. As I said before, if you were to take the derivative of this linear position change, then you would come up with a constant velocity and 0 acceleration, which is the definition of terminal velocity. Finally, what if? What if an object were thrown with an initial velocity? That would not change terminal velocity. You can demonstrate this by going to your code and setting it to display the ball's final velocity. Then you come up here, and that's in the print section, by the way. Come up here, edit the initial ball velocity in the vector right here, say an arbitrary number like -2 meters per second. Then we come down to the time, make that larger than what we currently have, just to make sure that the new larger drag coefficient has enough time to cancel out the initial velocity that's larger than the terminal velocity. Then we run the module, and we will see if we compare this to another run that final velocity does not change. So terminal velocity is not at all dependent on initial velocity, and that makes a lot of sense. If you look at our original equation, it's dependent entirely on when mass gravity is canceled out by the force drag. So in conclusion, if you look at our comparison chart, the Python with drag was an excellent predictor of the motion of the coffee filters. As a matter of fact, a lot of this discrepancy is actually a result of how you record position in tracker. The coffee filters become kind of hard to see as you go on, so this is in actuality a lot closer than it even appears here. So it is definitely an accurate model for the drop of coffee filters, and